These are all determinant -1. I mean, these are orthogonal matrices which are not special orthogonal. So somebody called it improper rotations. I don't like using that. Okay, so that's all.
We write a scalar as a whole number and with a unit. Similarly, how can I write a pseudo-scalar?
I gave an example, no? E dot B, for instance. That's an example of a pseudo-scalar. It does not transform under rotations, but under parity, it changes sign because E is a polar vector and B is an axial vector. So that's all. That's an example.
Okay, sir.
Okay.
I have one question. Sir, in the last class you told that a rotation vector that is invariant under the action of the matrix P is a pseudo vector. Sir, in this definition, can we use instead of P a general orthogonal matrix with determinant -1 instead of P?
Yes and no, because yes in a way, but we saw that every orthogonal matrix. I'm getting some echo. So every orthogonal matrix, now it's better. Every orthogonal matrix can be written as P times a rotation matrix. Okay. So a vector is not invariant under rotation. So you have to write it that way. P times. So if you know the transformation under P, you know the transformation under arbitrary orthogonal transformations. Okay. So request to people who ask questions is that if you have headphones, please put them on because otherwise I'm getting feedback.
Hello, sir.
Yeah. Yes, Bidhi?
Yes, sir. I have a doubt about contravariant vector equations. You have written that three vector equations mix with each other. Can you elaborate a little on this? Because there was a lot of confusion.
Yeah, sure. I don't know. An equation is a vector, so it transforms. So let's do that. So let me I'll just write something. Okay, can you see my screen?
Yes, sir.
Okay, good. Okay, so a vector equation. It's a set of three equations which we saw. I wrote it like this: EI equal to 0. Right? So I equal to 1, 2, 3. Under rotations, EI say goes to EI prime. Okay, which is equal to Rij Ej. So in particular, let's look at E prime 1. What is that equal to? R11 E1 plus R12 E2 plus R13 E3. So isn't the right hand side a linear combination of E1, E2 and E3, those three equations? That's what is the mixing I was talking about. Right, under rotations, E1 prime is not E1, no? It's some constant times E1 plus another constant times E2 plus another constant times E3. Is this clear?
Yes, sir. Yes.
This is what I meant.
Yeah,
okay.
Yes, sir. Thank you.
So, but one consequence of this is if you can see that if E1 equal to 0, E2 equal to 0, and we need all these three, this implies that E1 prime is 0. Okay, this has to do with the fact that it's linear. Linearity guarantees that. Okay, so if it vanishes in one frame, one thing, under rotation, it will vanish in the other. Okay, so this is.
Hello.
Yeah, go ahead.
Sir, I wanted to ask that yesterday you gave 2 questions as homework exercises to us.
Can we discuss that later? Some of them will come in your problem set, etc.
No, actually, I didn't want to ask you the solutions for them. I just wanted to ask if are we supposed to deal it on our own I mean, I was unable to do both of them. And
That's okay. That's okay. You can, so we can use the tutorial session,
oh,
okay,
okay.
to discuss that, or you can post your after. So Monday will be. So this is a good point to. We'll have a tutorial on Monday. You will receive your first problem set later today. I'll post it on Moodle. Okay. So, and videos will of course appear on Google Classroom. The reason I don't put it on Moodle is because of size limitations. And by the way, I do do some processing to reduce the size of the video. Okay, so Google Classroom, Google Meet gives a very huge file, and my files are like 1/3 or 1/5 of that. Okay, so that if few people download it, you have the number you'll have a smaller file to download. So these are some small tricks which I do. Okay, so good.
So you're saying that you're going to give the problem set today, later
Yeah.
today,
Yeah.
and we are supposed to do it in what time limit? What?
You have the weekend.
The weekend, and if you are unable
Friday,
to
Saturday,
solve,
Sunday. On Monday, yeah. Even if you don't succeed in solving it, that's okay. But what is important is that you try to solve it.
and on Monday we can ask doubts from that problem set.
Yeah. Absolutely, you can ask. Okay.
Thank you, sir.
So, any other questions, comments, etc.? Even that, the floor is open before I start.
Sir, do we have to submit the problem set solutions in a PDF?
That's a good question. So, some people they want to share. So what they do is they write their solution and send it to me before the tutorial, before Monday. You don't have to give solutions to everything. You could say, I'm going to give solution to problem 3 or something like that. Okay?
Yes, sir.
You're welcome. I mean, last year at least 5 to 6 students used to do that regularly. And sometimes I will discuss, I won't give my solution, I will discuss their solution or ask them to discuss their solution, some combination. Okay, so that's, yeah, you're welcome. I mean, I really approve.
Okay, sir.
Okay.
Thank you.
So today we're going to study symmetries of Newton's equations. Okay, and so let's just try to look at the second law. Okay, so this is the second law. Okay, and so the idea is so we need some. So first, and of course, first law is for when there are no forces. So we will define. Or we will say rather, we will say that two observers are mutually inertial if they agree on forces. On all particles, which formate. Okay, so this is the idea, and in particular, when no force is acting, on a particle, they agree on that fact. They both agree. Okay, so this is the idea. So, so now, let's go back and try to ask So consider two observers now. A and B, who are mutually inertial. Okay, and let's say that they choose coordinates. So A has coordinates x1, x2, x3, and time. We'll put time also there, let's see, the clock. B has x1 prime, x2 prime, x3 prime, and x3 prime. Okay, so the question which we want to ask, okay, what is the most general between the two coordinates, two frames. So we'll call we'll call this frame A, call this frame B, okay, between the two. Okay. So we are asking a very general question. What is the most general? So the idea is that we would like to write xi prime as a function of x's, xi's, or let's just, I'll hide the index here. So we want to ask what is this most general function. Okay. So first what we will do, so let's consider the case of no force on a test particle. Even mass is not relevant for this, but let it be this way. So what we would like is that, so equation in frame A will be m d square x by dt square equal to 0. And what should be the equation in B? Right. So what we want to do is we want to find out what is the most general transformation such that these two get related. So one implies the other. Okay, and you should, okay, so this is what we want. Okay, so let us go ahead and try to write some. I'll write something. So okay, so these two x's could be related by translations. Okay, but then we can also have some constant ui.
So,
Yeah, one second, go ahead.
So here the d square x dt square is representing the sum of all the forces in the frames, no? Means the sum of forces on all the particles in the frame.
I can always add all the forces and call it as one force. No, I don't care if there are 1 million things causing the forces. I don't care.
Okay.
That's a resultant force, right? Because I have only one, I'm focusing on one test particle. Right? We can do vector sum of all the forces acting on it at any given time, right?
Yes, sir.
Okay. But now I'm just looking at the case when it is 0, but actually, so suppose we have this kind of relationship. Okay, so let's mark all the parameters. So this is one, this is another, this is another, and this is another. Okay, So it's easy to check. So if you just go ahead and do this. So let's do that. First thing is that, say, so what is this? Let's start from here. What is this T naught? They have not agreed on, on the zero of their time, right? So when they start their stopwatch or whatever. Okay. So that's all. So this is just the shift of origin, but we are going to assume that the time ticks the same, etc. So T prime is equal to T plus T naught. Okay. So first thing we'll see is that we'll do this computation.
So should it not be ui into t plus t naught?
No, because the right hand side is only a function of t, right? So I want it to be a function of x and t. So so RHS has only frame a variables. Does it make sense? Okay.
Okay.
So
why is t prime not a function of x?
Hmm?
So why
You
is
can
t
go
prime?
ahead. You can try to add some function of x. You can try. Okay. Yeah. But then, so I'll do this computation, and if you can find some function which will satisfy, which will take you from here to here, I'm okay with that. Okay. D square x by dt prime will be dxi prime by dt times dt by chain rule, right? But dt by dt prime is 1, so I can just take derivative with respect to dt, and then you'll see that Raj is a constant matrix, so we'll just that. So what we get really is this is equal to correct. Now we do second derivative. Okay, I'll jump one step because dt by dt prime is 1, so this is nothing but d square x by dt square. So if you just do a calculation, this ui is a constant, it goes up, so it just becomes Rij d square xi by dt square. We get our final formula, which says okay. So this is what we get. So so you can see now that d square this implies, because this is just an invertible matrix, you can see converse also, because this is an invertible matrix, so I can take it to the other side. So arrow goes both ways. Is this clear?
Sir, in the right hand side, that is xi or xj?
It is xj, I just noticed that. Thank you. Okay. So is this clear? So yeah, if you want, I should also, I mean, if you want to be very pedantic here, we can even do this. We call this j. Okay. But anyway, it holds for j equal to 1, 2, 3, etc. Is this clear? So this is what we get. So adding forces. So what it says, if when so this is when this thing, but when there are forces, what we get so this equation, we multiply by m, left hand side will become fi prime equal to Rij fj prime. Fj.
So in the d square xj implication equation, one of them should be primed, right? D square xj prime. Yes, thank you, sir.
Thank you. Any more mistakes? Okay, very good. So when there are forces, it doesn't, I mean, it's not like says that the force, so this is just a statement. This is, we understand this is just that force. So this makes sense. Okay, so let's come back to the set of transformations I wrote, and so let's box it. Okay, so so now a claim, a set of transformations parameterized by Rij, Ui, Bi, sorry, I messed up. Okay, now it's fine. So the set rotation, we'll call this parameter the boost, Galilean boost parameter, and the other one is just a translation and time translation. Okay, is the most general one. So like somebody just said that can I put x dependence in the t? The answer is no. Okay, so just some parameter counting. So Raj has three parameters. We will see three independent parameters. Ui has three, Bi has three, and T naught has one. So there are 10 free parameters. And there are no more is what I'm saying. Okay. So this is kind of very nice. And so this transformation has a name.
Sir, Rij is a 3 cross 3 matrix, right?
Yeah, but it's not arbitrary matrix. It's a special orthogonal matrix. So we will see that a special orthogonal matrix is, I had one claim last time, right? It's a unit vector, some direction with an angle. So unit vector means that has two parameters, right? Because length is fixed to be 1. So it has two free parameters and the angle of rotation, that is 3. Or if you remember some Euler angles or something, there were 3 Euler angles there also. So Rij, if it were an arbitrary matrix, invertible matrix, it will have 9 parameters. Okay, but here what is happening is Rij is special orthogonal. Okay, so just the orthogonality condition is equal to 6 equations. You can check that. So it will remove 6 conditions on 9 free variables. So there are 3 remaining. Okay, so we will do this counting again, but I just want to get this in, and so I'll. Okay, this transformation is called a Galilean transformation. Okay, this is one thing. Other, R equal to identity, UI 0, 0. That means only is called a Galilean boost. Okay, what is a Galilean boost? So suppose what that says is that if you come back and look at this equation, where did I do the derivatives? Yeah, we did the first derivative, right? So Rij is just identity. So it just says that the particle at rest in frame A will be moving with velocity ui. Okay, so that means frame B is moving. The origin in frame B, if you wish, is the frame B is moving with velocity minus ui with respect to frame A. Okay, that's called a Galilean boost, but it's intuitively it's just that, it's just moving its uniform velocity, so it doesn't change. So these are called as Galilean transformation. Okay, so now we will see some properties, which is very, very interesting, and so for that I will have three observers. So A, B, C are mutually inertial. By that I mean A and B will agree on forces, B and C will agree on forces, C and A also will agree on forces. Okay, and so we already have coordinates for A and B, so I just need to write coordinates for this guy. I'll just put double prime. Okay, so let's now.
So does that mean that there can still be a force which is common to all three, making them non-inertial?
No. I mean, in particular, if A and B say there are no forces acting on a particle, C will also say the same thing. I'm not so good at sizing things, so let's do a better job. Not great, but better than improvement. Okay, so this is frame A with coordinates. Frame B, frame C, okay. So we already saw that there was a transformation which let you express B, xi prime and t prime in terms of a Galilean transformation. Okay, so we'll just write. So let's use some symbols. So this G takes you from B to A. But it's very easy to prove that A to B also should be some other Galilean transformation, which I write as G A to B. Okay. So G is short form for a Galilean transformation. Okay. Now, what about B and C? How will their coordinates be related? They will also be related by some Galilean transformation, right? They have to. So let's call it. This takes you from. I want to change the direction of the arrow. This goes from C to B. Similarly, there will be another one which goes from G from B to C. Is this clear? There's some, I mean, because they are mutually inertial, that must happen. But similar thing should happen even here, right? So if we look here, what should I call this? G, A to C, right? Similarly, there will be one other one, which I'll somehow, so let me just get rid of this. Go from C to A. Okay, is this clear what I've written? So we have a whole bunch of transformations.
Yes, sir.
Okay, so now let me, I need this picture, so I'll reduce the size. Okay, so now we can do, now let's do some things. So let's follow this guy first. This arrow. What does it do? It takes you G A to C directly, right? So G A to C. But I can do it in a slightly different way, right? I can go from A to B and then go from B to C. I should be able to do that also, right? So first I go from G from A to B. Then I compose it with G. These two should be the same, right? It shouldn't matter, no? Is this clear, what I've written?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
And
Yes, sir.
also I can do this. I can go from G B to A, sorry, G A to B and then come back. So I'll also have something like this. Should be nothing, right? Which is identity. It just comes back to itself. Okay, so these are properties that we will have. In fact, I can add a third guy also, a fourth guy, which is mutually inertial, and you can compose things, etc. But I mean, what this is saying, this is a very important property. What it's saying is that the composition of two Galilean transformations is another Galilean transformation. That's what this is saying. Okay, and it follows from this very, very physical observation. We are just saying A and B are mutually inertial, B and C are mutually inertial, so A and C must be mutually inertial. That's what it's saying. And we have seen that, I mean, only assumption is that if any two things are mutually inertial, they should be related by Galilean transformation. So this is a very important thing. So we'll call this closure. Right? So you compose them any number of times. Okay. So more generally, we could
This
have
should
something.
be
Yeah.
A to B, then B to C now.
Which
G
one?
A to C equal to this one. G
This
A
one.
to C equal to
Very good
this
question.
one.
No, wrong. Because first you go from A to B, and then in mathematics, this is how you write operations. No, what you do is first you do this, and then you do this.
Yes, sir.
So
Is that clear?
it is just like an operator, means first G A to B is acting, then on it G
Yes,
B
sir.
to
Yes, sir.
C is
Understood.
Yeah, because we are always what acts. I mean, this is how we write. Maybe if you were a Chinese or something, we're writing from, or Japanese or something, writing from right to left, then you flip things around. But we write from left to right. No, so the operations will go the opposite way, right? So this is standard mathematical convention. So I'm not.
Arabic also, sir.
Okay. So let's say that let D be let's add one more guy to make it even more messier, actually more interesting. Let D be another observer, that is with respect to A, B, and C. Okay. So now I can do things like this. So I can go G, change color for a moment. So G, A to D I can do. Now I can do this in the following way. G, A to B, then compose it with G, B to C, compose it with G, C to B. I can do it in 3 steps. But now I can do this in many ways. I can 2 ways I can do this. I should put brackets. So let me write this again and then put brackets. So I'll do this. So here what I'm doing is says you do this composition law, GB to C, GA to B, okay? And we can also do it this way. Okay, so we know this is equal to GCA. We know this is equal to GCA. And what is this equal to? GDB, right? B to D. We know that, but the order doesn't matter. What do you call such conditions? If you're multiplying, composing 3 things together and the order doesn't matter? Associative. Okay, it's called associative. So again, this is a very physical statement. I mean, you know that this A to D is some unique thing. So whatever way you do it, it shouldn't matter. So associativity also comes. Okay. And we'll just give one more name for this. So we'll just call this, so this just says that this is inverse operation. In GA to B, GB to A is the inverse of G to A, because you compose them, you get identity. Okay. So the amazing thing is that these properties are encoded in the axioms of a group a group in mathematics. Okay. So we got this from physical grounds, and so by the way, this picture, whatever I've drawn here, still, I mean, this is completely a very very physical statement. But thing is, we will find that there will be modifications to Galilean transformations, which will come later in special theory of relativity. But this picture will still hold. Okay, so what we mean by G will change a bit. But all these properties which define something called a group already exists in mathematics. And the biggest advantage of this is that mathematicians are, they have some rigor, and then they want to come up with a concise set of axioms. Okay, so which will define something, and we have seen all of them. So I'll give the definition. So this is a mathematical. The definition of a group okay, let G be a set. Okay, And so we can write G would have elements G1, G2, G3. Okay, by the way, I've written it as a bit as discrete elements. It can have infinite number of elements. It can have continuous set of elements. Just some set, just a collection of these things. And dot be a binary operation. That takes any two elements and gives another. Okay, so suppose G1 and G2 are elements of G. Then this dot means you compose them, and that gives you another element of G. Okay. So now I'll give the axioms. First axiom is the closure axiom, which I've just written here. For all G1, G2 in G, there is G1 dot G2 belongs to G. Okay. Then there is something called an identity element. Okay, before that we should write associativity. Third is existence of something called an identity element. Okay. There exists an element, special element E, which belongs to G, such that G dot E equal to E dot G equal to G for all G. And the last one is the existence of an inverse for any G, little g, is an element in G. There exists a unique element that we denote by G inverse, such that okay, so let's look at let us look at that. So now Galilean transformations form a group. So what is the set? G is the set of Galilean transformation. Okay, and what is dot? The obvious composition that we had here, that we were discussing.
Hello?
Okay, yeah, go ahead.
Sir, is there any difference in writing associativity before then identity? I mean, why were we conscious about that?
Right. No, because associate, I need to introduce an element called identity. I need to introduce some special thing. For associativity, I don't need any extra ingredient to add. So that's the only reason. So in that sense, it comes before.
Okay.
Okay, so now you can see that all, so the Galilean group is the following: G equal to the set of all Galilean transformations.
So this E element is not unique.
So it is unique.
E.
Okay, and dot is the obvious composition of transformations. So G dot is the Galilean group. Okay, so SO3 is a set of 3 by 3
Excuse me, sir.
special. Yeah, go ahead.
Sir, can you zoom out a little bit?
Zoom out.
Oh, yes, sir. No, I meant make it smaller.
Smaller. Oh, you want to see more. Is this okay?
Yes, sir.
Now I'm just giving you another example. I'm giving the set of special orthogonal matrices. And what is dot? This is matrix multiplication. Okay. So this is the row. It's also a group. Okay. So similarly, O3 is also a group. The set of orthogonal matrices with det equal to -1 is not a group. Why?
Closure not satisfied.
Yeah, closure, because product of two guys. Okay, so SO3 works, O3, the full group works, but you can't have the determinant -1. Okay, so now we'll give some more trivial examples. Set of integers, and the operation is addition. With multiplication now.
Inverse of 0 doesn't exist.
So inverse doesn't exist. Not just 0. What is inverse of 2?
Inverse of, yeah, inverse of
Inverse doesn't
all
exist.
doesn't exist.
Okay, so, and yeah, so, but we should actually ask what is identity in this? What is E in this? Z plus is a group. What is E equal to?
0.
0.
0.
Okay, here what is E in 6?
1.
1.
1.
Okay, so you can see that it depends on the set and etc. Okay, so yeah, so we can do this. We can take rational numbers Q and X is still not a group, so I'll put a star. Okay, so Q, this is rationals. That means numbers of the form P over Q. Okay, rationals without where P and Q are integers. Rationals without 0. Is this a group?
Sir, rationals with zero or without
Without zero. Without zero. I said.
Sir,
I said.
आपने with zero.
Yeah, I know. Sorry. This is a group.
Yes, sir.
Yes, sir.
Okay. So, but I mean, so you can see that groups are actually all around us, and this, so groups naturally appear as symmetries in physics. Okay. So this is a very, very nice thing, but I just want one more definition. Okay. So let's say that G and dot is a group. Okay. If G1 dot G2 is equal to G2 dot G1, so order doesn't matter for all, or any G1 and G2 which belong to. Okay, we say the group is commuting or abelian. Okay, otherwise it is non-abelian. Okay, so let's go back here and ask questions. Okay, what about Galilean group? Do you think it's abelian or non-abelian? Is it abelian?
No, sir.
No, it's not. Rotation group?
Yes.
Yes, sir.
No, it is not. It's non-abelian. Order matters. O3 also is non-abelian. What about Z plus?
Yeah.
Abelian.
Yeah, it's brilliant.
It's abelian, sir.
I'll give one more example. SO2 is abelian. Check. So I'm done for today. So today what we have seen is that if you look at the symmetry of Newton's equations, you end up with this group which is called the Galilean group, which has a bunch of properties, and some of the properties you will study. Composition rule is something very interesting, and so you should work out the details of how the composition. So you take two different Galilean boosts, that will be part of your assignment, and you compose them, and you should reorganize it and show it as it's equivalent to another Galilean, so not Galilean boost, general Galilean transformation. It will become a third Galilean transformation. So how are the various parameters related? Okay, so this is something which we should do, and so the floor is open for questions now.
So, in the very start, when we defined the function for xi prime,
Yeah.
so we didn't take the function to have any inputs of xj squared because we need to preserve the homogeneity of space. But sir, why do we not take any function of xj dot?
No, it's a property of the frame. Okay, but xj dot would be a property. I don't want. Somebody please mute yourself. Okay, so no, I mean that is not a property of the frame, right? Because the velocity is a property of this thing. So it's more you should think in terms of frames, and so that's not the property.
And so for x square also, it's just like not
X square, what is X square?
So xj square. Why is there no term for xj square or xj cube?
It won't work. It won't work. I mean,
So,
first thing is, I mean,
uh,
you want this to hold, right? I mean, these kind
so
of things.
as far as I was under the impression that it was done due to the preservation of homogeneity of space, because if you have a square term, the value for xi dash would
No,
depend.
I'm just solving a stupid mathematical equation. I am saying, I mean, there are other fancy ways of getting it, but I'm not saying that is wrong or anything. I'm just saying I write something like this.
Okay, sir. So we'll take
And
it
then
as a
ask,
property of the problem.
okay, that's all I'm asking.
Okay, sir. Thank you, sir.
Okay, what I'm saying is that if you put any quadratic terms and all, it will not work.
Okay, sir.
Just will not
So,
happen.
hello, sir.
Yeah.
So, can you scroll down? You had said that SO3 is not an abelian group since the order in which we rotate matters.
No, if you compose, it's more under, you take two different rotations. I mean, it's very easy, right? You take, you do something which is, you take something and rotate by 90 degrees along rotation about z-axis and then rotation about y-axis, and then do the other thing, you will see it won't work.
But sir, if we do the same for small rotations, doesn't it?
No.
Isn't it true for? Means, isn't there?
No, it's not
okay,
true.
Sir. Okay,
it's
okay,
not true. It's not true. Unless you do, rotation, in the same direction twice. You rotate by angle theta and theta 1 and theta 2, and then you do it's equivalent to rotation by theta 1 plus theta 2. But same axis. So
okay,
it's not.
So you said that groups naturally appear as symmetries in physics. So which symmetry of right now have we used for the Galilean?
Newton's equations.
So which symmetry was?
So it maps, I mean, this was the point. I mean, the map, I mean, this is what we wanted. For me, this is a symmetry in some sense. It says that is this. Yeah. This goes to this. The same. The form is not. It's covariant. Or more like this. This is what.
Okay.
Okay. So you can go to quantum mechanics and look for symmetries of the Schrodinger equation. Non-relativistic Schrodinger equation. You can do that. Okay. But that will be a problem in quantum mechanics. But you will get the same answer.
Thank you, sir.
Sir.
Yeah.
Here you have written the transformation equations for xi dash and t dash. So was this a hit and a trial method? Like how did we arrive at this?
Okay. So I mean, actually, it's really extremely simple in the sense that you can what you will have, the most general solution to something like this. D square x by dt square equal to 0, so that will have only these kind of terms. So you can a little bit of jiggling you need, but it's not something deep. You can okay.
Yeah, it was just the solution. We tried to solve
Yeah.
Yes. Thank you, sir.
Yeah, I don't think I proved that this is unique and etc. I have not proved it, but that's something which it depends on how mathematically inclined you are. But one can prove that.
So here we're trying to solve for symmetries and find the transformation, and then searching for which type of mathematical group it is it is contained within. So why do we do it? Means why does the group matter in physics?
Yeah. Okay. Great. So can you remember this? And when we finish this course, you ask yourself this question, and you're going to give us the answer. Okay.
All right, sir.
Okay, so I mean, actually, somebody was pointing out a few things, right? You expect things to be isotropic, homogeneous, blah blah. All these things, these are constraints we put in, and then that implies certain things cannot happen. So, but why do we put that? You could ask those things. Yeah, but yeah. So symmetry turns out to be a very important. So we will see things in this course like symmetry implies conserved quantities. That's a different, I mean, this is more like symmetries of some. So first thing is we are assuming we can write some differential equations which which describe our system. And then what we are saying is that we are asking for transformations which preserve that form of the differential equation. That's what we are asking in a particular way. And we are calling that the symmetry of the differential equation or symmetry of the system. Okay.
Sir, in G group, what exactly that E element is?
Okay, it depends on the content. I mean, it's just any set.
Yes, sir, G,
Mathematicians don't care.
G2.
For them, it is just some set. And you can, so they have classified, for instance, suppose G has 10 elements. Okay. So given that all these properties, you can ask how many sets, how many groups with 10 elements exist. Okay. It turns out, I think the answer for this is 2. Okay. So when it's power, so for instance, 8 is very complicated. There are 5 different possibilities. But if it is prime, if order of G is prime, then there's only one set.
Sir, G
There are
A to
weird
B
things.
dot G B to A.
Huh?
Sir, G A to B dot G B to A and let's say
that is
D
no.
to
I
A
thought you were
dot,
asking about general group.
those two are E.
Repeat. Now repeat your
Sir,
question.
G A to B dot G B to A. That's one thing. That's E.
Yeah.
And another G A to D dot G D to A.
Yeah.
That's also E.
Yeah.
So how
Because
it
then
is
they differ because what you do first and what you do second. So if you look at this here, I'm going from A to B first and then coming back from B to A. But if you look in the different order, if you switch the order, you're starting from B, going to A and coming back to B. So they're different that way. Okay. Okay, let me just stop recording now. Just one second.
One last doubt.
I'll stop the recording, please.
Okay.